Welcome to the lecture series on deep learning in neural networks. This video covers the vanishing gradient problem. In the previous part, we have studied the forward path of backpropagation. Let us now look at the backward path. This is the path of backpropagation of errors. Suppose for a given pattern we have a delta, a mismatch in the output of 0.5. Then this delta is propagated backwards to the previous layer, from there to the previous layer, and from there further on through the whole network. So here again the formula of the update step of the backward path in backpropagation. The deltas in layer n-1 depend on the deltas one layer further up in layer n, and we sum over all weights that connect layer n-1 to layer n. But these sums are multiplied with the derivative g prime evaluated at the value. So if the activation is alpha, the g prime of this sigmoidal unit would be small. If it's epsilon, the g prime would be close to 1. For piecewise linear units, ReLUs, it's different. There, if the value of alpha is large, then the g prime is always 1. Okay, so this is the update from the transmission from layer n, deltas in layer n, to the deltas in layer n-1. Suppose now we do this across many layers. Then at each layer we have to sum over the different paths. And in the end, if you want to update something down here, the deltas down here depend on all the possible paths. And each path now contributes a g prime in the first layer, a g prime in the second layer, and so forth. So if you want to update weights in the first layer, we have n-1 multiplications, we have n-1 factors g prime. Now the point is, if only one of these values g prime is 0, the whole path does not contribute. If none of them is 0, but 2 or 3 of the g primes are very small, if you multiply 0.1 with 0.1 with 0.1, the contribution is also negligible. So many of these paths that run backward will not contribute, or will contribute only a very tiny term if the network is deep, which means if the number n of layers is large. And this is called the vanishing gradient problem. The gradient does not arrive at the bottom of the network if the network is very deep. So if you want to update a weight in layer 1, we have to backpropagate delta errors over many layers, and we have to sum over many paths, but each single path contains many factor g prime. And the risk is that no information arrives. So let's look at this g prime. If you have a sigmoidal unit, then g prime is small out there. So if you have a value of alpha or an activation value, which is norm of 4 or larger, even 3 becomes critical. If you have an activation that is large, then the g prime basically vanishes. And that means that if somewhere in the backward path there is one g prime which is small, the whole path does not contribute. On the other hand, we have seen in the previous part that the nonlinearity in the forward path for sigmoidal units requires that for some patterns the activation is out of the linear regime, which means a must be larger than 2. The absolute value of a must be larger than 2. Now, this imposes some constraints because those units that nicely contribute to the nonlinearity are those that sometimes don't contribute to the gradient. Let's now look at the same thing for the ReLU. In the ReLU, the G prime vanishes whenever the activation is below 0, which means whenever the neuron is not active. So if we consider a forward path and there's an inactive unit, then this unit will not contribute to the output, but then this unit will also not contribute a G prime on the backward path. So on the other hand, the G prime is equal to 1 for all ReLUs that sit on active paths during the forward pass. So in a way, for ReLUs, the highly active forward paths coincide with good gradient transmission on the backward path. So, second point for ReLU. So note again that the nonlinearity argument considers a distribution across different patterns. So a successful forward pass needs to avoid the linearity problem because in a neural network we need to exploit the nonlinearities. The successful backward pass needs to avoid the vanishing gradient problem. And so, if we choose hidden units, then this should be our guideline. A good hidden unit must be good for the forward and for the backward pass. And the ReLUs are a good candidate for this. So let's again finish with a quiz. First claim: the forward propagation with ReLU leaves only a few active paths. And yes, this is correct. This is correct because all ReLUs that are inactive contribute to 0 and the forward propagation kills that path. Second claim: backpropagation with ReLU leaves only a few active paths. And again, this is correct because on the inactive paths the G prime is 0. Third claim: forward propagation with ReLU is always linear on the active paths, in the sense that we sit on the linear part of slope 1 of the ReLU. And yes, this is correct. In a ReLU network, all patterns are processed with the same linear filter. Think about this. Well, no, this is wrong. Different patterns probe the ReLU units at different activation values. Some sit in the 0 slope value, others sit in the slope 1 value. Next claim. Let's now turn to sigmoidal units. In a network with sigmoidal units with small weights and normalized inputs, all patterns are processed with the same linear filter. And yes, this is true. They are all processed with the same linear filter. This is the linearity problem. In a sigmoidal network with big weights, there are active units in the forward path that contribute a vanishing gradient in the backward path. And yes, this is also true. So again, second point for the ReLU, because in the ReLU the forward pass and the backward pass identify active units that contribute equally on both passes.